Hello viewers, I welcome you all to the presentation on solvent extraction and in which let us understand in this module how the uncharged metal chelates are going to be extracted and what are the equilibrium principles which are involved, how to regulate the selectivity of extraction of the metals by treating with the chelating agents, and thereby we can enhance the selectivity and extraction efficiency of the extraction of these uncharged metal chelates. In the previous two modules, we have discussed about the extraction systems, how the molecular systems are classified into different systems based on the equilibrium principles involved during the extraction process. So the extraction systems can be classified into essentially covalent neutral molecules, uncharged metal chelates, and ion association complexes. In the previous module, we have discussed about the extraction of essentially covalent neutral molecules. What are the factors which affect the extraction efficiency and hence the selectivity of extraction of essentially covalent neutral molecules? We have given some examples and how to regulate the selectivity, how to enhance the selectivity of extraction, and what are all the experimental factors we need to optimize during the extraction of such essentially covalent neutral molecules we have discussed. So in this particular module, let us discuss about how the uncharged metal chelates are extracted. Initially, the metal complexes will not be uncharged, will be charged. If the metal complexes are charged, the extraction of metal complexes will be impossible. So as I told in one of my previous modules, any analytical system, if you wanted to extract into the organic phase, their aqueous solubility must be minimized. That means analyte must be made less hydrophilic and that has to be made more hydrophobic. If the species are charged, the hydrophilic property of the analyte will be more, and hence the extractivity into the organic phase will become lower. It is highly impossible. Therefore, charge neutrality is very important. This charge neutrality can be attained by treating any metal complexes which is having some particular charge with a selective reagent in order to convert that metal chelate or metal complex into uncharged one. So what kind of reagents which are used, how these reagents will contribute their role in extracting the metal chelates in the uncharged form, and what are the equilibrium aspects which are involved in the extraction of such uncharged metal chelates, we shall understand in this particular module. So uncharged metal chelates, I have presented here some typical examples. So any metal complex, if you take, metal complexes are obtained by sufficiently hydrating the metal ion in the aqueous phase. We know water is a versatile ligand in order to get complexed with various metal ions, irrespective of the charges. So when you dissolve any sample containing metal, water molecule will be coordinating with the metal in order to form a coordination complex. Of course, complex might have formed, but the metal complex with water may not be uncharged. So we have to convert that metal complex into uncharged complex. Then only that uncharged metal chelate or uncharged metal complex can be extracted into the organic solvent. So I have presented in my previous module about the structure of some chelating agents such as acetylacetone, 8-hydroxyquinoline, and dithiazone. These are some selective reagents in order to complex metals such as iron, zinc, lead, bismuth, tellurium, palladium, cadmium, copper, etc. So when you use these metal hydrated complexes with such reagents, the charge neutrality takes place in order to get water insoluble or aqueous insoluble complex and organic soluble complexes are obtained. So therefore, these chelating agents are going to be very, very important to consider in forming uncharged metal chelates. So here I have presented the three examples: iron acetylacetone complex, zinc 8-hydroxyquinoline complex, And any metal, if you take among zinc, lead, bismuth, tin, nickel, palladium, this diphenyl thiocarbazone will be a selective reagent to complex. If you look at the structure of these complexes, these are not having any charge. These complexes are not possessing any charge. Therefore, these metal chelates, because they are having the chelating structure, the ring-like structure is present for these particular complexes. Therefore, these complexes are present in chelate form. Why the chelated forms are obtained? Because we have used the chelating agents such as acetylacetone or 8-hydroxyquinoline or dithiazone or some other reagents. Therefore, if you use such chelating agents and if you extract hydrated metal complexes, we will get uncharged metal chelates. So these uncharged metal chelates will be extracted into the organic layer with high efficiency. So what are the equilibrium aspects involved in extraction of such metal chelates in their uncharged states? We have to understand in this particular module. So, metal chelates have to be uncharged in order to extract them into the organic solvent. If the charge neutrality is not attained, the extraction of such metal chelates is impossible. So, how to convert them, charged metal chelates into uncharged metal chelates? We have to use a reagent. A typical reagent has to be used. And once this reagent is used, the ionization or any further chemical transformation of this particular reagent should not contribute to the efficiency of the extraction. Means the reagent should not be getting extracted into the organic phase. So only we are interested to extract the metal chelate in its uncharged form. So the reagent must influence the formation of the metal chelate which is charged into uncharged one. So the metal chelate in the uncharged form must be able to be extracted. When we treat this metal chelate which is having charge with the reagent, such a reagent we need to use. So what kind of a reagent we have to use? Of course, the reagent must be weakly acidic, and acidic reagent should undergo ionization, and after ionization it will be converted into cation and anion. And metal water complexes, metal complexes with water are charged, they are positively charged. So we need an anionic reagent in order to neutral their charge, metal chelate. So metal complex in water is positively charged. We need an anion in order to neutralize the positive charge of metal complex. So therefore, anion should participate in the charge neutrality. So charge neutralization will be done by the anion of the reagent what we will use. And this reagent may also contain the hydrophobic group so that the hydrophilic property of the metal complex can be reduced once the metal complex in water reacts with this particular reagent. The hydrophobicity will be enhanced. As a result, as a result of the enhanced hydrophobic property of this metal complex that will be extracted into the organic layer in the complex form. So this is very important. So while treating the metal complexes in water in the aqueous medium, that means to say, when you dissolve any sample containing metal, any metal it may be, water will be a versatile ligand, and the ligation takes place to convert that metal into metal complex with water, aqueous metal complex that will be charged. So that will be treated with a suitable reagent, and that reagent may be weakly acidic or weakly basic. Even that such a type of reagents can also be considered. The reagent will be used in such a way that the anion of the reagent after dissociation should participate in the charge neutralization. Therefore, charge neutralization takes place, not only the charge neutralization, but also due to the hydrophobic group present in the reagent that will make the complex less hydrated. The binding between the metal and water molecule will be will be weakened. Therefore, the hydrophobic property will be enhanced to the metal complex. Therefore, it can be extracted with better efficiency. So several equilibria are involved in the formation of such uncharged metal chelates because we have to neutralize the charge, and after neutralization we will extract that what are the equilibrium principles or what are the equilibrium aspects which are involved in formation of such metal complex which is uncharged. So we have to understand. So in order to understand this, let me generalize that reagent what I am using here. I said it is a weakly acidic reagent. So consider it is in the form of HR, H indicating the acidity. So HR is a reagent which is a weakly acidic reagent, monobasic reagent, and that will ultimately dissociates in water to produce H plus and R minus, and HR in the undissociated form will be able to be getting extracted into the organic phase. So therefore, it will also possess the ability to distribute in organic and aqueous phase. So here I have presented the chemical reactions. So when you take this HR in the aqueous medium, water is a suitable medium in order to initiate the dissociation reaction. So the reagent HR undergo dissociation to get converted to H plus and R minus. So if you use equilibrium principle, the dissociation constant will be concentration of H plus ion into concentration of R minus ion divided by concentration of the reagent. So in the aqueous phase, because dissociation takes place only in the aqueous phase, not in the organic phase. So in the organic phase, dissociation will not occur. So even as I told you, HR may also distribute between the organic layer and the aqueous layer too. So partition coefficient according to the distribution of this reagent is simply the ratio of the concentration of the reagent in the organic phase to concentration of reagent in the aqueous phase. So this is according to partition equilibrium principle. So let me assume we are interested to extract this metal hydrated complex, MH2OX N+. Here N plus is the charge, X indicating number of water molecules coordinated with the metal to form this complex. So a metal complex MH2OX N+ has to be converted into uncharged metal chelate, and that has to be extracted into the organic layer. So how to do this? So let us assume this metal hydrated complex having N plus charge reacts with R minus. Here R minus is obtained by dissociation process, and this reacts with R minus, and then it will form an uncharged metal chelate, that is MRN. So this is possible in the aqueous phase. This reaction will be possible in the aqueous phase. So metal complex in water which is having N plus charge will react with the reagent R minus. Number of moles of R minus required are N, that is going to be MRN plus XH2O. Because this is a complexation reaction, the equilibrium constant for this complexation reaction will be Kf. MH2OX N plus is positively charged species and R minus is the negatively charged species. Positively and negatively charged species combined together. This is a metal, this is containing metal ion, and this is the reagent in order to form an uncharged metal chelate, that is MRN. And because this is a complexation reaction, the equilibrium constant for this complexation reaction is Kf. So even here law of mass action can be used. The equilibrium constant Kf is equal to concentration of MRN in the aqueous layer divided by concentration of the metal ion complex in water in the aqueous layer into concentration of the reagent to the power n in the aqueous layer. So according to law of mass action, the equilibrium expression has been written here. So Kf is the formation constant for this complex formation reaction. Because MRN is uncharged, MRN is uncharged, and whatever the amount of MRN form, that must be able to be transferred into the organic phase in the extraction process. So when you extract the aqueous layer with a suitable organic reagent, organic solvent, so organic solvent will become a suitable solvent to transfer MRN from aqueous layer to organic layer. Therefore, MRN has the ability to distribute between aqueous and organic phase. So if you use Nernst law, Nernst partition law, MRN will distribute. Therefore, partition coefficient of MRN, that is KDC, C indicating complex here, MRN complex, KDC is equal to concentration of the uncharged metal chelate in the organic layer MRN divided by concentration of uncharged metal chelate MRN in the aqueous layer. Therefore, KDC is equal to concentration of the uncharged metal complex in the organic layer divided by concentration of uncharged metal complex in the aqueous layer. You can write this. This is in accordance to Nernst partition law. So we know in place of KD, we can write D. KD will not reflect the total concentration of the analyte. Whether you consider aqueous layer or organic layer, the total concentration of the analyte has to be considered. If you take aqueous layer, in the aqueous layer, metal may be present in the hydrated complex form or in the MRN form. We don't know what is the quantity of the metal which has been converted into MRN, uncharged metal chelate, or if there is any metal present in MH2OX N+ form. So we have to consider the total amount of the metal, total concentration of the metal which is present in the aqueous layer. In the meantime, in contrast to the presence of metal present in the aqueous layer, in the organic layer, MRN will be the only species which will be present in the organic layer because MRN is more soluble in the organic solvent. Therefore, that will be selectively transported into the organic layer very selectively. Therefore, the distribution ratio for this particular complex is simply written as the ratio of the concentration of the uncharged metal chelate to the total concentration of the analyte in the aqueous layer. So concentration of the uncharged metal chelate will be MRN in the organic layer divided by MRN concentration in the aqueous layer plus the free metal hydrated complex in the aqueous layer. The denominator indicating the total concentration of the metal in the aqueous layer or in the aqueous phase. Okay. So after having this particular complex formation reaction, after converting the metal, hydrated metal into uncharged metal chelate, we should have some conventional assumptions. So what are those assumptions? So apart from MRN, let us assume apart from MRN, the concentrations of chelated species are negligible. Apart from MRN, the concentration of other chelated species are negligible. Means we must assume and we must ensure that either in the aqueous layer or in the organic layer, apart from MRN, nothing should be present. If there is anything present in the uncharged metal complex form, that will also contribute to the extraction. So extraction efficiency will become uncommon. Extraction efficiency will become inaccurate in such cases. So this is the first assumption. Let us assume the concentration of the chelated species other than MRN are negligible. So apart from this MRN, either in the aqueous layer or in the organic layer, other chelated species are absent. Even they are present, their concentration is very, very less. Next one. The concentrations of hydroxy or other anion coordination complexes are negligible because if these anion coordination complexes are present, they will contribute to the ligation. They will contribute to the ligation. Therefore, further complexation process may be possible if the free metal is present. If the free metal is present, further complexation process is also possible. Therefore, we have to make sure that the hydroxy or other anion coordination complexes are not present. Even if they are present, their concentration is quite negligible, we have to assume. Okay. And the important other assumption is the reagent HR we will use in order to convert metal ion into uncharged metal chelate. So HR will be used and the chelate MRN is formed. So once MRN is formed, either HR or MRN should not undergo dissociation. Either HR or MRN should not undergo dissociation. Here, we are concentrating to extract only metal in the form of MRN and we are using HR as a reagent to form MRN. So whatever the HR dissociated, that will contribute R minus to form MRN. Therefore, MRN is the only species to be extracted into the organic phase. because HR is weakly acidic species, if it is not dissociated to the major extent, unreacted HR may also getting extracted into the organic phase. So HR and mRN, the reagent in the undissociated state and mRN in the undissociated state might have been extracted into the organic phase, and the concentration of metal complex, uncharged metal complex in the aqueous layer must be negligible, because the concentration of mRNA in the organic layer we are going to consider. This must be more in order to obtain the highest value of D. When do we say the extraction efficiency is maximum? If the maximum amount of the complex, if the maximum amount of the analyte has been extracted into the organic phase, then only we will say the extraction efficiency will be more. Therefore, in the organic phase, if you consider HR and mRNA are present in the undissociated state, and in the aqueous layer, the concentration of mRNA is very, very negligible, very, very less, very, very less. So, under such circumstances, by using these three important assumptions, we can write the distribution ratio expression as D is equal to Kf into KDC into Ka into concentration of HR to the power n in the organic layer divided by KDR into concentration of H plus to the power n in the aqueous layer. According to dissociation equilibrium and the partition law, Nernst partition law, and the formation constant expression, we can arrive to this simplified equation, that is Kf into KDC into Ka into concentration of HR to the power n in the organic phase divided by KDR into concentration of H plus ion to the power n in the aqueous layer will be giving you the value for distribution ratio D. So where Kf is the formation constant for the formation of mRN complex, KDC is the partition coefficient for the formation of the metal chelate, Ka is the dissociation constant for the dissociation of reagent HR, KDR is the partition coefficient of the reagent HR. Because HR undergo dissociation, H plus ion will be produced. Its aqueous concentration is also very important to consider. HR will undergo dissociation. It will dissociate to produce H plus ion and R minus ion, because R minus ion reacted with metal ion to form mRN. Therefore, the only species left over is H plus ion. So, because of the H plus ion present in the aqueous layer, the acidity of the aqueous layer or aqueous phase, if you simplify this further, D is equal to K star into concentration of HR to the power n in the organic layer into H plus ion concentration to the power minus n in the aqueous layer. Here K star indicates Kf into KDC into Ka divided by KDR. Kf into KDC into Ka divided by KDR is given a new constant, that is K star. That is K star. So this is the important equation. If you look at this equation, D is equal to K star into concentration of HR to the power n in the organic layer into concentration of H plus ion in the aqueous layer. So for a given reagent, what is the reagent we have used? HR. And the solvent. The extraction of the metal chelate in the form of mRN, we will use HR reagent in order to convert the metal into uncharged metal chelate. So the extraction of that metal chelate is dependent on the pH of the aqueous layer, because hydrogen ion concentration is involved in the aqueous layer. Hydrogen ion concentration has to be considered. As the hydrogen ion concentration will be more, pH of the aqueous layer will become less, right? So the extraction efficiency or the selectivity of the extraction of the metal chelate is dependent only upon pH, and what concentration of the reagent we are using. So concentration of the reagent and the pH of the aqueous phase will become very important here to play the role. Okay, but if you look at this equation, the distribution ratio for the metal chelate is independent of the initial concentration of the metal. Here MH2O x to the xn plus is not present, it is absent. So the distribution ratio, the extraction of the metal chelate is independent of initial metal ion concentration. There is no metal ion involved in this expression. And in other words, if you look at this equation, if we use the reagent in a constant and excess amount, if you use this reagent in a constant and excess amount, the concentration of HR to the power n in the organic phase will become insignificant. That will also become constant. That will also become constant. And we can ensure by this, we can ensure all the metal has been converted into mRn. Because HR we have added to the aqueous layer before the extraction process is made on. HR has been added in excess. Whatever the amount of HR required to complex the metal has undergone dissociation. So complete amount of the metal, overall amount of the metal has been converted into mRn, and hence that has been extracted into the organic layer. So therefore, the concentration of HR and pH are the two important factors in order to efficiently extract the metal in the form of uncharged metal chelate. So therefore, if we consider this as a constant, in an higher amount it has been added to the aqueous layer, D is equal to K star dash, because HR concentration to the power n is also constant. So that will be multiplied with K star. So we will get a new constant K star dash into concentration of H plus ion to the power minus n in the aqueous layer. So this is the equation in an alternate to this expression. You take log on both sides. Log D is equal to log K star dash plus n into pH. Log D is equal to log K star dash into H plus ion concentration to the power minus n in the aqueous layer. This will be in the form of log D is equal to log mn. So log mn will be log m plus log n. Here log n is log concentration of H plus ion to the power minus n. So that will be minus n log of concentration of H plus ion. So you will get pH. So plus n into pH you will get. So log K star dash plus n into pH. Log K star dash plus n into pH if you simplify this after taking log. So where log K star dash is equal to K star dash is equal to Kf into KDC into Ka into concentration of reagent divided by KDR. KDC is a partition coefficient for the complex and KDR is the partition coefficient for the reagent. So metal complex, KDC is a partition coefficient of the metal complex. KDR is the partition coefficient of the reagent HR. Kf is the formation constant of the metal complex. Ka is the dissociation constant of the reagent. Okay, so we know the relationship E is equal to 100D divided by D plus 1 when we use equal volumes of aqueous and organic phases. In order to calculate the percent efficiency of the extraction, we know E is equal to 100D divided by E plus 1. 100D, E is equal to 100D divided by D plus 1. So if you simplify that, you will get D is equal to E divided by 100 minus E. So you take log for this equation on both sides. Log D is equal to log E minus log of 100 minus E. Simple. You take log on both sides. Log D is equal to log M minus log N, where M is E, N is 100 minus E. But we know that log D is equal to log K star dash plus N into pH in the previous slide here. Thus, log D is equal to log K star dash plus N into pH, which is equal to log E minus the log of 100 minus E. So here log D is equal to log K star dash plus N into pH is very, very significant. In what way? It is very important to understand here. So suppose you assume you are going to introduce any extraction step. You are going to use any extraction procedure for the extraction of analyze metals present in a sample, and metals may be monovalent or divalent or trivalent. This N is indicating the valency of the metal which you are going to extract after its conversion into metal chelate. If N is equal to 1, monovalent metal. If N is equal to 2, divalent metal. If N is equal to 3, trivalent metal you are going to use. So log D is having direct influence on pH, N into pH. So if you look at this, log D is having direct influence by the pH. The pH to be monitored for the extraction of monovalent metal will be more when compared to divalent and when compared to trivalent. The pH to be regulated in order to extract the trivalent metal will be less. At lower pH, trivalent metals will be extracted with better efficiency. So as the N value is increased, the efficiency will also increase. So trivalent metals will be extracted at lower pH than the divalent, than the monovalent. So N is equal to 1, 2, 3, the valency of mono, di and trivalent metals. Okay. So according to this equation, you have this equation log D is equal to log K star dash plus N into pH, which is also equal to log E minus log 100 minus E. Here, this plot is very important to represent the relationship between percent efficiency of the extraction as a function of pH in the extraction of monovalent, divalent, and trivalent metals. How the extraction efficiency will be varied with respect to pH. So here N into pH for monovalent ions, the range of pH in order to achieve 100% extraction is very wider, the range of pH. Because N is less, as I told you, for monovalent metals, the range of pH to achieve 100% extraction will be very wide. And for divalent metals, the range of pH for the extraction of metal ion, which is divalent, the range of pH will be lesser when compared to the range of pH for monovalent ions. And it is very less for trivalent ions. The range of pH in order to achieve 100% efficiency, the range of pH to be regulated will be very less. So the pH range will be very high for monovalent ions than divalent ions, and then trivalent ions will be having very less pH range. So pH in the x-axis, there is no significance to be given for the pH values. So they have written incompleted 246, 246, 246. So pH versus percent extraction, if you see the curve, M plus ion means monovalent ions, M2 plus divalent, M3 plus trivalent ions. If you look at the steeply raised values for percent extraction, it is rapid for trivalent ions when compared to divalent, and divalent ions are having rapid values when compared to monovalent ions. Therefore, the percent efficient extraction of trivalent ions can be made by monitoring the pH with lower range. Okay, so let us assume the pH off. pH off is nothing but say the extraction of any metal is selective only upon appropriate fixing of the pH for the aqueous phase. If we are able to fix the pH of the aqueous phase to an appropriate level, then only we can extract with better efficiency. So 100% extraction is made, that is at pH. pH off means, let us assume not 100%, only 50% of the metal is extracted. That is the pH. pH off is pH at which only 50% of the metal is going to be extracted. Then this can be used to assess the degree of separability of two or more metals. pH off can be used in order to assess the degree of separability of two or more metals. When two or more metals are present together, how the degree of separability can be assessed, how the selective extraction of one metal can be enhanced without getting extracted the other metal. So we know this equation, log D is equal to log K star dash plus N into pH. So log E minus log 100 minus E is also equal to log D. So log K star dash plus N into pH is equal to log E minus log 100 minus E. At 50% extraction means E will be equal to 50. You just substitute. Log K star dash is K star dash plus N into pH is equal to log 50 minus log 100 minus 50. So log 50, log 100 minus 50 is also log 50. So log 50 will be cancelled. So you will get 0. So log K star dash plus N into pH will be equal to 0. So log K star dash is equal to minus N into pH of. So log K star dash at 50% extraction of the metal will be exactly equal to minus N into pH of. So you got now log K star dash is equal to minus N into pH of. So we have also know the equation that log D is equal to log K star dash plus N into pH. So log K star dash is minus N into pH of. You substitute this value in this particular equation. So log D is equal to minus N into pH of plus N into pH. You take N as a common factor. N as a common factor, log D is equal to N into pH minus pH of. N into pH minus pH of. So if there are two metals are present in the sample solution, we need to understand the separation factor. Separation factor means one analyte must be extracted with greater efficiency without extracting the other analyte. If two metals are present, we have to concentrate on only metal to be extracted with greater efficiency than the other metal. So from separation factor, beta is, we know, beta is the separation factor. It is the ratio of D dash divided by D double dash, where D dash is the distribution ratio for metal 1 and D double dash is the distribution ratio for metal 2, where D dash must be significantly greater than D double dash. So if you take log beta, logarithmic value for both sides, log beta is equal to log D dash minus log D double dash. Okay. If we do extraction at specified pH, because extraction of metal ions selectively solely dependent upon the pH of the aqueous layer. pH of the aqueous layer. So log beta is equal to, we know log D, log K star dash plus N into pH, or log D is equal to N into pH minus pH of. So at specified pH, log beta is equal to log D dash means N dash into pH minus pH of dash. N dash is the valency of metal ion 1. pH of dash is, this is a pH for the extraction of 50% of this particular metal having valency of N dash. Minus log D double dash means N double dash into pH minus pH of dash. N double dash is the valency of the second metal and pH of double dash is pH for 50% extraction of this metal having valency of N double dash. All right. You assume N dash will be equal to N double dash. If you assume the valency of the two metals are same, valency of both the metals are same, that is the metals are having the same formal valency, then what do you get? Log beta is equal to N into delta pH. Let us write pH minus pH of dash is equal to delta pH. pH minus pH of dash will be equal to delta pH. So N dash into pH minus N dash into pH, they will be getting cancelled. If N dash is equal to N double dash, N dash into pH will be coming here. Here also N dash into pH, they will be getting cancelled. Then N dash into pH of dash plus N dash into pH of double dash minus N dash into pH of dash plus N dash into pH of dash, you will get delta pH of. Simply we will write N into delta pH of. So log beta is equal to N into delta pH of. Right. So this N into delta pH of is very significant here. Before that, for any selective extraction, as we discussed from selectivity of extraction, beta value should be at least 10 power 5, greater than or equal to 10 power 5. Then only we can say one metal will be extracted, one analyte will be extracted without making the other species getting extracted parallelly. So if beta value is 10 power 5, log beta will be 5 for one extraction. If you do only one extraction for a species which is present in the aqueous phase along with other species, and the beta value, if it is the ratio of D1 divided by D2 is 10 power 5, then the log beta will be 5 if you do only one extraction. Then delta pH of is very significant here. If a monovalent ion is present, delta pH of will be equal to 5. If a divalent species is present, delta pH of will be equal to 2.5. If a trivalent species is present, delta pH of will be 1.7. So 5 into 1, 5, 2.5 into 2, 5, 1.7 into 3, 5. So N into delta pH is very important here. N into delta pH, it is very important here. And that value will be giving you from the slope of the graph what I have showed in one of my previous slides. The slope for this particular plot for the monovalent ion and the slope for this particular divalent ion and the trivalent ion, you can see the slope will be more for trivalent ion and the slope will be less for divalent than the trivalent, and the slope for monovalent ion will be lesser than divalent ion. If you look at the slope for trivalent metal will be more, and slope of trivalent metal will be greater than the divalent. It is greater than M plus ion. So this N into delta pH of is very, very important. If beta is greater than or equal to 5 for one extraction, delta pH will be 5, 2.5 and 1.7 for mono, di and trivalent metals. What does this mean? So what is the use of this? Very simple. Selectivity by pH control is greatest. So any metal you are going to extract, whatever the valency, whether it is monovalent or divalent or trivalent, the greater selectivity can be achieved provided you have the knowledge to regulate with the pH. You are having the ability to adjust appropriate pH for the extraction process. Therefore, according to this equation and according to the graph, trivalent metals can be extracted with more selectivity than monovalent, as reflected by the slope values. So trivalent metals can be extracted with greatest selectivity than monovalent ions because the slope value is more for trivalent ion. N into delta pH of value, you can see that is only 1.7. Delta pH value is only 1.7. The change in pH in order to make trivalent ion from for the extraction of that particular metal from aqueous phase to organic phase, we have to change the pH only 1.7. That's it. That's what the slope is more, and the range of pH will be less, and the curve is very narrow, very steeply raised. And for divalent, it is more when compared to 1.7. Similarly, for monovalent, it is more when compared to 2.5 and 1.7. Therefore, the selectivity of extraction by regulating, by controlling the pH for trivalent ion will be more when compared to divalent, and for divalent it is more selectively extracted when compared to monovalent ion. That is the significance of this curve. So slope is directly proportional to selectivity of the extraction. So let us go back to one of the equations, that is D is equal to Kf into KdC into K into concentration of Hr to the power n in the organic layer divided by KdR into H plus n concentration to the power n in the aqueous layer. So we know the value of beta. That is D dash divided by D double dash, where D dash should be significantly greater than D double dash. So that is also equal to Kf dash into Kdc dash divided by Kf double dash into Kdc double dash. D dash is equal to Kf dash into Kdc dash. D double dash is Kf double dash into Kdc double dash. We know this by our basic knowledge. If beta is insufficiently large, what does this mean? If beta is insufficiently large, the quantitative separation of any metal or any solute is controlled by pH. If beta is sufficiently large for one solute, pH is the only factor we have to play. The aqueous phase pH is very, very important in order to extract one solute with the greatest selectivity. Selectivity is reflected by the value of beta, and selectivity will be coming only in case of the sample systems which are having more than one kind of analyte. So pH is the factor. Apart from this, the extractability of any metal is not only dependent on pH. Even in some cases, pH is not sufficient to regulate the selective extraction of one particular metal. Even at that particular pH, the other metal which is also present may also be getting extracted. In such cases, we may have to use masking agent. So what are these masking agents? Masking agents are simple chemical reagents. They will form strong complexes with one metal. And this complex will be water soluble. That's it. Masking agents are the chemical reagents or masking complexing agents. Assume there are two metals are present in the aqueous sample solution. Without using masking agent, by monitoring a suitable pH, if you do the extraction, both the metals are getting extracted, maybe getting extracted. In such cases, we will use masking agent. So masking agent is a reagent in which in the extraction process, it will react with one metal to form a water soluble complex. Therefore, masking agent will shift the extraction curve for the metal which has been converted into complex to the higher pH value. So at lower pH value, the metal which is left over in the uncomplexed form will be extracted. So therefore, that will be extracted first. And the pH for the extraction of the metal which has been masked by using masking agent will be more. So at higher pH, this metal will be extracted. And at lower pH, the other metal which has not been masked by using masking agent will be extracted. Therefore, if you consider the formation constant for the complex formed between this metal and the masking agent is KFM. For metal 2, it is KFM double dash, and for metal 1, KFM dash. So beta is equal to KF dash into KDC dash into KFM double dash divided by KF double dash into KDC double dash into KFM dash, where K dash Fm and K double dash Fm are the formation constants for the metal complexes with masking agent, and you must assume that K double dash Fm is greater than K dash Fm. So according to this, either by controlling the pH and by using the masking agents, we can extract one metal by retaining the other metal, and hence the selectivity of the extraction can be achieved. So this particular slide is reflecting some common chelating agents which are used to extract. These are all the metals which are belonging to the group of beta diketones. So they are acetylacetone, phenyl trifluoroacetylacetone. I will show you the structure of these chelating agents. These two are used for the extraction of beryllium, tin, chromium, manganese, and molybdenum. Oxime means 8-hydroxyquinoline and its derivatives are used for the extraction of aluminum, magnesium, strontium, vanadium, and tungsten. Alpha dioxymes such as dimethyl glyoxime and alpha furyl dioxymes are used for the extraction of nickel and palladium. Dialkyl dithiocarbamates are used for the extraction of bismuth, thallium, stibnium, antimony, tellurium, arsenic, selenium, tin, vanadium, etc. Dithiazone, that is diphenyl thiocarbazone, is used to extract lead, mercury, copper, palladium, etc. And cuferan is the trivial name. It is ammonium salt of N-nitrosophenyl hydroxylamine. So it is used for the extraction of iron 3, gallium, antimony 3, titanium 4, tin 4, hafnium, zirconium, etc. And pan means 1,2-pyridyl azo 2-naphthol is nothing but the pan. It is used for the extraction of uranium, indium, vanadium, palladium, zinc, cadmium, manganese, yttrium, etc. 1-nitroso 2-naphthol is used for the extraction of copper, nickel, and cobalt 3. Therefore, these are the metals which can be extracted by using these chelating agents. That means if you treat these metals, the aqueous complexes of these metals with these reagents, they form uncharged metal chelates, and uncharged metal chelates can be extracted into the organic solvent with greater selectivity. These are the structures of acetylacetone. Phenyl trifluoroacetylacetone. Phenyl means thiophene. Phenyl means from the second position of the thiophene, there is a keto group for the attachment. 8-hydroxyquinoline, dimethyl glyoxime, alpha furyl dioxime, again at the second position of furan, attachment will be taken place. Dithiazone, diphenyl thiocarbazone, ammonium salt of N-nitrosophenyl hydroxylamine. So hydroxylamine, N-nitrosophenyl hydroxylamine, ammonium salt of N-nitroso, N double bond O is nitroso, hydroxylamine, phenyl hydroxylamine, and 1,2-pyridyl azole 2-naphthol. This is 1,2-pyridyl azole 2-naphthol, and similarly 1-nitroso 2-naphthol. So to recap, in this particular module, we have discussed various equilibrium principles which are involved in the extraction of metal chelates by converting them into uncharged metal chelates, and how to regulate the selectivity of one metal while masking the other in the extraction process. So thank you for your patience for listening this particular module.